Okay, so a very good evening and welcome to today's live interactive session. In today's session, we will be mostly discussing on the uh, erosion protection, how we use geosynthetic for this erosion protection purposes. All those things we will be discussing. Actually, today's whatever has been taught in week 11 lectures, those that are not like too much. Like there are very less problems related to that available. So whatever problems are there, some of the problems are there. We will be trying to solve them. Very easy and basic problems. Uh, and I don't think that would take much time and effort. So those are problems are quite straightforward and easy. So we will be trying to solve some of those problems after we just recapitulate how whatever was taught in the 11th lecture that we will be going through. And as we have a lot of time, what I'm thinking is that we can recap the week 10th, whatever we had solved some problems and we discussed some problems regarding filtration and drainage. So those problems we can just go through once again, so that because this filtration, all these things are also quite similar to that. Right, so what we can do, I will just share the screen, share the part presentation for the previous week. We will just in say half an hour, 45 minutes time. Slowly, we will just go through whatever we had solved in the previous class. We will just try to recall everything, and then we will come to this erosion part and see some erosion protection problems. And yeah, so that will be all about today's uh, session. And in the next session, we have a final topic that is remaining. That is our the use of these geomembranes. Okay, the geomembranes are generally used for these landfill liners and all these things. So some portions we will be discussing in the next class. Okay, so what are the main properties that we should know, design properties of geomembranes that we should know. Okay, there are some basic, like very basic properties such as water vapor transmission, permeance, all those things. So we will discuss all those things in the next class, and then we will be seeing some basic problems on how to decide the embedment length and all those things. We will decide then how to decide the covering. Okay, so when we place a geosynthetic liner, so you have to cover it with the soil. Okay, we have place a soil cover over it. Okay, so that the geosynthetic stays in, so that the geomembrane stays in position. Okay, so you have a slope, right? So you have a tank, you have a slope. So you are putting the geomembrane to make your this landfill. Right, so above the geomembrane, we put some veneer. Veneer means as covering, soil covering. So how to reinforce that, how to design that veneer. So you will be solving some problems in the next class regarding that, which will be on the 17th next week. And on probably on 18th, that is not sure. So one more, just 1 hour discussion session after that, after the 12th lecture we will be having. Maybe probably on 18th morning we will be having that. Just 1 hour, we will just revise whatever we have taught, we have studied from the first week to the 12th week very fast. We will just revise whatever have been taught, so that you can just recall all the concepts in 1 hour stretch of time. Okay, we'll do that very fast. It will be a fast paced. We'll finish that in 1 hour. So probably that will be on 18th or 19th or whatever, that will be informed. And on the 17th, we will have the 12th lecture. And probably on 18th, that time that will be informed. That time we will have the summary session of 1 hour duration. All right. So as we have time, so let me do one thing. Let me just share the screen of the this previous weeks. Okay. So I hope it is visible. So I hope it is visible. So let us see what we studied. So we already studied means how to design a filter, right? So what are filters? So filters prevent the passage of soil and allow water to pass through it. So that is the basic purpose of filter. Okay. So to uh, avoid clogging and to allow free flow of water, right? So to retain soil particles and to allow free flow of water, and while doing that thing, while stopping the soil and while allowing free flow of water, the filter should actually do not get clogged itself. Okay, throughout its design life, it should not get clogged itself. So that should be satisfied. Okay, so some important soil parameters that you should know. We all know this CU and CC, how to get this coefficient of uniformity and coefficient of curvature for any soil that we can get from the grain size distribution plot that we know. Then there are many criteria. So basically there are two segments of criteria, right? One is the retention criterion and another is the permeability criterion. So retention criteria of a filter actually prevents the piping of soil, that is the loss of soil, and the permeability criteria actually ensures that there will be proper flow of water to the filter. Okay. So generally we can use either you can use geosynthetic filter or you can use aggregate filter. Aggregate filter means what? So just arranging some uh, proper size of aggregates so that those aggregates actually stop the loss of fine particles and allow the flow of water. Or what we can do, we can use geosynthetic materials such as geotextile. Okay, such as geotextile, which will actually prevent soil and allow water to flow through. So there are some basic differences. Those were discussed and they are mentioned here, right? And what is actually this apparent opening size? AOS O95 actually, not O90. It's actually O95, O90. Sometimes it's O95 is actually called AOS, sometimes O90. So generally O95 is actually called apparent opening size. Okay, O95 is the apparent opening size. So these are some of the properties of the geotextile that we should know. Now there are many criteria that are given by many researchers and many papers and many codes, but none of these criteria are actually which you cannot definitely with assertion you cannot say that these criteria will work for my kind of soil. Okay, sometimes it may work, sometimes it may not. So, but in general, these some of the criteria that are mentioned are actually given here. Okay. So you see, this is a German criteria. So then we discussed this type of soil where for a particular soil we knew the D10, D50, D60, D90 size and we were to select a suitable geotextile filter. Okay, so since the D50 of the soil, since the D50 of the soil lies between 0.02 and 0.01, we are saying that this is a problem soil. And for problem soil, here we have this criteria, geotextile selection criteria that is given. So we just put CU here. So you find out the coefficient of uniformity. We put it here, so we get 0.26, and then from here we get 0.25. So lesser of the two we will take. Okay, now this is a very important test known as the gradient ratio test. So what is a gradient ratio test? A gradient ratio test we already discussed this previously also. So in gradient ratio test, what we do, we actually establish the compatibility between a filter and the soil. Establish the compatibility between the filter and the soil. Uh, so we need to ensure that the geotextile that we are using, okay, the geotextile that we are using with the soil, with our soil, that both of them are compatible. That means the soil should not actually means soil should not actually, there should not be loss of soil to the geotextile, that it is the filter should work properly. The filter should allow adequate passage of water through it. Also, we need to ensure that the filter is not getting clogged. Okay. So to establish this compatibility, so generally we do this gradient ratio test. Okay, this was discussed. So you can see here with time, initially what happens? Initially, the permeability of the system reduces. So as there is a soil filter formation, so initially it is high permeability. After that, permeability will reduce a bit. And after this soil filter is formed, so the a separate filter is formed actually with the help of soil particles. Okay, so say we have a filter. Okay, so here we have soil. So what happens as there is a flow, the soil forms a bridge here, bridge, or it forms a layer. So that soil actually forms a soil filter also. Above this geotextile filter, its soil also forms a filter. Okay, so so after the formation of soil filter, okay, after the formation of soil filter, we are seeing that the system permeability actually becomes constant. And also, initially, there are a lot of soil particles will get get passed through the filter. So, a lot of soil particles will get piped. So, but after that, we are seeing that after as time passes, this piped particles weight of soil pipe will become zero. Okay, so here we are saying that in this region, this equilibrium has been established. Okay, so then we discussed some problems regarding this design. Okay, filter design, how to select filter. So here we have a 3.5-meter high Gabion wall consisting of 1 meter into 1 meter into 3 meter long baskets. Okay, so sitting on a 0.5 into 2 into 3 meter long matrices shown here. So this is shown here. So these are the baskets, Gabion baskets, and here we are putting some filter. Yeah. Okay, geotectile is a filter. So the properties of the soil are given, T10 size is given, coefficient of uniformity is given, T85 is given, the permeability is given, the relative density is given, all the properties of the soil are given. We have to check the adequacy of three candidate geotextile are given here. So we are actually to check the adequacy of these three candidate geotextile. Okay, the cumulative reduction factor is also given. So what we have to do, so we have this uh, Cape one, right? So what we need to do is we need to draw this in a proper scale and then try to construct the flow lines and equipotential lines. Okay, so why are we drawing these flow lines and equipotential lines? That is because we need to find out the total flow Q. Okay, so first we need to calculate the required permittivity. For that, first we calculate the flow KH FIN, the number of flow lines 4, number of retention 5. The K is this one, total head is 3.5. So get the Q, right? Get the Q. Then what we do? Then we calculate the permittivity. So what is the permittivity? K by T. K by T is nothing but Q by delta H2. So what is the head loss? 3.5. Area is 3.5. So uh, this is the lane, right? And water is flowing like this. So what is the area through which water is flowing? Height times per meter length, right? Height 3.5 each 3.5 times per meter length. So 3.5 into 1. So we get the required permittivity as this much. Then for geotextile 1, 2, 3, 3 geotextiles, these ultimate permittivities are given. Those ultimate permittivity you convert to allowable permittivity by dividing by this reduction factor. Right? And then what we do to determine the factor of safety, we have the allowable divided by the required. So allowable divided by required will give us the factor of safety, and you can see these are the factor of safety that we found out. These are more than sufficient. Okay, very high factor of safety we are getting. So this was all about the permeability criteria, right? The flow criteria. Then we need to establish the retention criteria. So there are many retention criteria as I already mentioned. So one of them is Carroll's criteria. So Carroll's criteria says the O95 should be less than, that is the apparent opening size should be less than 2.5 of the T80 hydrosoil. So according to that, the O95 should be less than 0.375 mm. Then we match with the given geotextile. So we see that this non-woven needle punch and this non-woven heat bonded, those two are satisfying our criteria. 1 and 3. So geotextile 1 and 3 both are accepted. Just a second. Yeah. So then we decide we solved a problem where we had to design this geotextile filter. Okay, this is a geotextile. So this is a pavement. Below the pavement we have the stone base. So water coming, so rainwater so coming here. Okay, it will come to the stone base. So we want that this water, whatever it is coming into the stone base, that should water should drain out through this under drain. But we need to ensure that the stone soil in the stone base is not lost, right? So what we need to do, so here we have an under drained, perforated under drain covered with crushed stone, and above that we have put a geotextile. So this geotextile will actually act as a filter that will allow the water to pass through it, but will prevent the soil, fine soil from the soil separate. Okay, we will prevent this fine soil from the soil separate to actually enter and then clog this under drain. Okay, so will prevent the soil from the soil separate to enter and clog this under drain. Okay, so you need to design this. Similarly, the properties of the soil are given and the candidate geotextiles properties are given, permittivity and separate opening size. So same, so first we choose the flow that might be occurring. So just they have taken 15 meter cube per day meter. This amount of flow will occurring per day. Then we find out the required permittivity, same like before. So what is the head 0.45? It's here is 0.45, and this is entering through this length, right? So 300 mm area, zero point 0.3 into 1. 0.3 is this side and 1 out of plane. 2.3 into 1. So here we get the required permittivity. Then we find out this allowable permittivity, and then again similarly we find out the factor of safety. Okay, we are seeing that the factor of safety in flow is 45, which is acceptable. Okay, so now to for the retention criteria, there are many criteria available. So what criteria to choose? So this is one table. Okay, you know, literature et al. So this is one table which we can refer to, the one chart we can refer to. So for our soil is actually what? See, what is the CU of the soil? CU of the soil is 5, which is greater than 3, and the relative density is 80%. So if you see in the chart, so you can see this for CU greater than 3 and for relative greater than density greater than 65, we can take this criteria here. Okay, so we choose this criteria. So 095 required should be less than 18 by safety. From here we get that O95 should be less than 0.126, but the given geotextile is a O95 of 0.212. Thus, we cannot use this, use the given geotextile in our case. So we need to choose some different geotextile. Okay, so this was all about filtration. Then we come to drainage. So what is drainage? Drainage is to allow the water, just to allow the water to pass through it. Okay, water to pass. So say we have a pavement here, right? So we have a pavement and we have side drains given here. So what we want, the water that it is entering to the pavement should flow through this geotextile and then follow the camber and then drain out in the drain. Okay. So for these purposes, actually these geotextiles are provided. So there are many applications that are given a pavement edge drains, interceptor trenches and slopes, drainage bed apartment. So there are many uses. So there are many. So what we can do, we can make a geocomposite like outer. We have the outer cover and inside generally we have a core which is in drainage. So there can be many types of core that we can do. So if you remember this uh, PVDs, okay, PVDs that we use, prefabricated vertical drains that we use, that had a outer covering, okay, outer covering, and inside we had a core. So outer we had a geotextile and inside that we had a this corrugated PVC sheet kind of thing, right? So that was the core and that core actually carried the water. Similarly, what we can do, we can put this outer layer and inside we can have a core. So outer layer will actually act as a filter and outer layer will allow only water to enter and prevent the soil to enter and the core will actually carry the water through it. Okay. So there are many types of core that are possible. So steep extruded intersecting ribs, that is this is the geonet. And you can single or double cascaded sheet, trees, snap, three-dimensional boxes. So many times of core we can. Okay, surrounding the core, we have some geotextile which actually acts as a filter. Now, in drainage, actually, whatever what is important is our in plane flow, right? So this is the geotextile. So the flow is occurring in plane. Within the within the plane, this soil is occurring. And within the uh, plane, this flow is occurring. So this in-plane drainage capacity is actually governed by this property known as transmissivity, theta. Okay, transmissivity theta. So this flow is occurring through what? This length, this width times this thickness of the geosynthetic, right? So that's why you see W into T here. Okay, and K into T is nothing but the transmissivity that we can see here. And there are many ways to calculate transmissivity. One is this constant head test. Okay, there are many ways. And one more important thing that we should note here is that this theta will actually reduce if the thickness reduces. So if the loading is high, say the normal load on the geotextile is high, what will happen? This thickness is going to reduce. If the thickness reduces, obviously this theta is also going to reduce. Okay, that is this theta is actually dependent on what? Dependent on two things. One is the uh, it's gradient, okay, gradient, and also it's mostly dependent on the normal pressure that is acting over the geotextile. Okay, yeah. Okay, so these I have given a table where there are some uh, this range of these reduction factors. Okay, the range of reduction factors that we can use for different application purposes. Okay, so there are five types of reduction factor. Right, there are five types of reduction factor. Just a second. As I was saying, there are five types of reduction factor. One is the soil clogging and binding. Then you have the creep reduction of voids and intrusion into voids, chemical clogging, and biological clogging. Okay, these are the five types of reduction factor that we need to use, and that varies from the ranges of these values varies with the application. So just an approximate value data given. Uh, then these are for, so this was for geotextile and this is for geonet. So in geonets there are four reduction factor: intrusion, creep, chemical clogging, and biological clogging. The soil clogging binding is not changed. Okay. Okay, then we solved some problems regarding this drainage function. Okay, we solved some problems regarding drainage function. So here you can see we have a earthen dam. In the earthen dam, we have a clay core. And in that clay core, what we are doing is that we are providing a geotextile here, so that the water that will seep inside that should flow through this geotextile and then ultimately drain out. Okay, so we need to find out the factor of safety for the flow. So how to find the flow? To determine the flow, again, what you need to do, we need to draw the flow lines and the equipotential line. So here you can see the flow lines and the equipotential line. So 1, 2, 3, 4, 5 flow channels, and how many drops? 1, 2, 2 equipotential drops. So from that you can determine the flow. So you see we have determined the flow here. And what is the gradient of flow? Sine for 75 square. How much? So how to find the gradient of flow? This flow gradient is nothing but what? H by L. What is the H? What is H is the water head and L is the length of flow. So here length of flow is what? Length is this one, this inclined length where the cursor is moving. You can see because the geotextile is placed along this length. Okay, so that is the length. So H by L you can actually get by taking sine 70. Sine for 75 is what? Is H divided by L. Opposite by hypotenuse. Opposite by hypotenuse. Opposite is H. Is H head and divide by L. So sine 75 will actually give us the gradient of flow. Okay. So gradient of flow we found out by taking sine of 40. Then we find out the required permittivity, which is KT Q by I into W. So 1.5, this one we found out by I. What is I? I is 0.97 and into 1. 1 is the per meter width. So Q theta required, we find out there. Finally, we find out the factor of safety theta level by theta required. So ultimate by reduction factor by required. So all these values are given, we just put and we just find out the factor of safety. Okay, we got the factor of safety as 3.22. So actually this is quite low. So generally we need a factor of safety of 5 to 10. So we need to choose the geotextile accordingly. After this, we do the retention analysis, water retention test check criteria. Etc. Then one more problem is solved where we have this what? This is a retaining wall. Deliver retaining wall. Behind the retaining wall, we have a non-woven needle punched geotextile acts as a for drainage purposes. Okay, and for same similar to the previous one, but this also we have to draw the flow lines and equipotential lines and then find out this flow. What is the gradient? One, obviously, because it's straight. Then we find out theta, similar vector of safety, which comes out as very, very low. It is not acceptable. Okay, comes up as very low. Generally, so we will try this problem again with a geometry. Okay. So here was another problem. So here we have a frozen food storage building where the temperature is less than 0.5 and the groundwater table is there, and so it was observed that there is upward capillary flow of water. So if the water actually reaches this portion, okay, and the temperature here is very low, right? So what will happen? The water will freeze. So due to freezing of water, if water freezes, it's going to expand. Okay, it's going to expand, and what? It will actually damage the structure. Okay, it will actually cause problems. Right, so what we need to do, we need to arrest the water before it reaches the building, and we need to drain that water out. So for that, we have under drains here. So water is flowing out. So water will be arrested here by the geotextile. Then it will be drained out to the under drains, and then under drain will be drained. Okay. So for this purpose, so this Q is actually taken. This much value is taken. Then we have 5% flow slope. It's given here, say 5% gradient. And so this theta required we find out like this. Then spectroscopy. So it is also coming quite less. It is not acceptable. So we need to choose some different geotextile. Okay, so this is the same problem as the previous problem. So here what we are doing here instead in place of geotextile, what we do, we are placing geonet here. Okay, and you can see one chart is given. So as normal stress is increasing for a particular gradient, you see that the flow rate also reduces. Okay, so we need to find out what is the average stress that is coming here, normal stress that will be coming onto this geonet, and as as per that normal stress, we need to find out the flow rate of the geonet. So similarly from the flow lines and equipotential lines, it's the flow net. We found out the Q value, that is the flow value. I is the gradient. Theta allowable, we find out as much is the theta allowable or the theta required actually. This is the theta required. So this is the theta allowable. Theta allowable or theta required, whatever. Then we find out the average normal stress. So half into 8 into 18, assuming gamma is 18, so you get 72 kPa. Now corresponding to 72 kPa, an I of 1, approximately we get, so I of 1, this is the curve. So something somewhat here we will get the flow rate. Okay, the flow rate is taken as 0.094 meters square per that we convert to meters square per second. Then we reduce this ultimate to allowable value by using appropriate reduction vectors, cumulative reduction vector. Then we find out the vector safety. So here also we see that it's marginally acceptable. Okay, not that much acceptable. So this was all that we solved in the previous class. The problems. So quite a lot of number of problems, but these problems are actually very straightforward and easy, right? So now what I'm going to do to share the screen again. Okay. So just give me a minute. All right. So let us start. So what is erosion? What is erosion? So erosion is nothing but process of detaching of soil particles from the ground and transporting it away. So uh, so due to wind, due to rain, due to waves, okay, there can be many agents. Due to that, what happens? Soil particles actually get detached from their native position and they get transported away, right? So generally erosion, uh, what are the susceptible places, right? Slopes, right? Slopes are frequented with erosions, right? Due to rain, what happens? Rain actually triggers erosion. After that, if the slope failure also occurs, okay. Then we have wind. If say high cyclonic winds are there, it can actually transport huge amount of soil from one portion to other portion. Then we have river currents that erode river banks. Huge, that is a huge problem. River erosion is a huge problem where actually it is seen that river is actually trying to change its course and it's eroding the settlements. Many houses, many mm, these establishments are actually lost. Okay, many establishments or settlements that are there along the river bank that are lost. Okay, so this is a huge problem. This Majuli River, Majuli Island, in which is the largest river and island. Okay, it's situated in Brahmaputra River. So the area of this Majuli River Island has reduced by huge amount. Okay, area of Majuli River Island has reduced by huge amount, all because of erosion due to River Brahmaputra. Okay, so due to River Brahmaputra action, eroding action, this this is taking the soil of the island with it. Okay, so there is huge amount of erosion. That is a huge problem in Majuli. Many people have lost their homes. The area is also reducing. Also, whenever there is floods in any river, the river expands, swells, and that time also there is huge amount of erosion taking place. Right. So in Majuli, what they are doing is that they are many like they are trying with many type of use this techniques such some of them are like using geobags, geopipes, all those things they are using. So to this prevent, just try to at least not prevent, you cannot prevent it completely, but at least try to reduce it to some extent. Okay. So as I said, soil on slopes is most subject to erosion. And as we know, it takes more than 100 years, okay, 100 years to form 1 centimeter of soil naturally. So we have to protect the soil. The problems due to soil erosion, loss of land, loss of the shoreline. Okay, loss of shoreline. So what happens, say, uh, is after due to cyclones, what can happen? This or cyclones or to the action of this sea waves, the shoreline gets on reducing. Okay, the water actually takes the shore away with it, and this shoreline actually gets receded. Then you have slope instability, loss of top soil and fertility of soil is also hampered. Then loss of reservoir capacity due to silting. Uh, uh, reservoir capacity means what? Say you have a dam. Okay, you've constructed a dam reservoir. So what happens? This river is actually carrying lot amount of silt. Okay, from the upstream side. So this when the river flows, it carries this silt from the surrounding, from the nearby river banks with it. And that silt actually gets deposited as the river from up as it comes down. Okay, in the downstream portion. Okay, mostly this happens in this hilly regions. What happens when from the hills, not hilly regions, I mean that rivers originating from glaciers. What happens initially, the river is very fast, right? The velocity of the river is very fast when it is up in the mountainous region. The velocity is very fast, so it carries all the field, everything, all the soil from surrounding banks with it. It erodes them and it carries with it. And when it comes to in the plains, come to the plain region, the velocity this reduces velocity of the river reduces, and what happens? All the silt actually settles down, and this actually reduces the capacity of the reservoirs. Okay, say if constructed a dam, it's going to reduce the capacity, holding capacity of it. This is also a uh, big problem. And rubber and tea plantations. So actually, I belong to Assam. So tea plantations are actually very predominant here. Tea cultivation. So tea is generally planted over terraces, right? So terrace. So terrace farming is done. So it's not terrace actually. It's planted on slopes. Okay, so tea is generally planted on slopes. So what happens as uh, these are planted on slopes, and if there is erosion, so due to heavy rain, okay, heavy rain generally, what happens is topsoil gets eroded, washed away very easily. The topsoil is generally very fertile. So what happens is gets washed away. Somewhat these plants actually hold the soil, but if the these forces are too high, water forces are too high, this gets washed away. Okay, so then it is a problem. Now, what are the different types of erosion forces? So, one we have this aeolian erosion. Okay, so what is aeolian erosion? Aeolian erosion means erosion due to wind. Okay, so when wind blows, fine cohesionless soil actually get eroded. So generally this happens say uh, in the beaches. Okay, beach you have sand, right? So if there is strong winds are blowing, okay, due to cyclone or something, what happens? This sand, this cohesionless sand, like so, this carried with the wind, with the heavy wind to over long distances and deposited somewhere else. So this actually happens. This is called aeolian erosion. Then you have rain erosion. It's very general, but whenever there is rain, this rainwater washes away water, soil with it. Then we have river erosion. Okay, river erosion is there. Then marine erosion, then glacial erosion. Okay, so marine erosion means what? These waves caused by waves. So waves also cause erosion on the shoreline, right? So that is marine erosion. Glacial erosion means when the glacier actually flows, moves along the slopes, this actually erodes the slopes on the sides. That is actually glacial erosion. So you can see here wind erosion. For wind erosion, this wind speed direction, type of soil, all this large exposed area, this all this lead to wind erosion. And see if you have small particles, okay, small cohesionless particles less than 0.42 mm in size, we can see that they are highly erodible. Okay, and say we have very large particles, say small boulder 6 centimeter is like small just pebbles or something like that. And if we have that greater than 6.4 mm, this little bit large. Okay, 6.4 mm. I thought centimeters. 6.4 mm is very how much? Very small, less only. Less than all are less than 1 centimeter. So very still, if it is less than 6.4 mm, then these are non-erodible. Then we have rain induced erosion. Okay, so here this rain is classified. Okay, based on this intensity and this droplet diameter. So what are the different protection system that we may actually employ? Okay, so what are the different protection systems that we may employ to prevent erosion? So one is riprap. Okay, riprap. What are riprap? So let me just see if I can. I will just share if I can. Uh, just see once. Huh? Just a second. Let's see if I can get. Actually, not there. Okay, whatever. So deep traps are nothing but, see, we put graded some boulders or a boulder, okay, graded boulders of different sizes on the shore, river bank, okay, river bank or shoreline, so that what happens whenever this water is hitting it, it helps in dissipation of the energy, okay, energy due to that water, and it protects the soil from actually flowing with the water. Okay, so this is repressed. So we'll see the images. Then we have concrete lining. Okay, just lining of concrete. Say we have a canal. We are having a canal. So this canal, sometimes we can have canal made just with soil, right? So that those kind of canals are more susceptible to what? Susceptible to erosion. The soil will get eroded. The slides of the canal will start getting eroded as water starts flowing. But if we line the canal with concrete by just spraying concrete or just putting a thin plaster of concrete over it, the bottom, that can prevent the erosion. The canal. Okay. Then we have this garnetting. Garnetting nothing but this spraying of concrete. Okay. Then Gabion mattresses. You know already know what are Gabions. Right, so Gabion mattresses you can use. We can put this large size aggregates in, say, uh, what to say, these steel wire meshed cages. We can fill them inside and we can make mattresses with them. Those are called given mattresses. Then we have geotextile covering. So geotextile covering, these type of geotextile covering are generally like regularly used to protect slopes. Okay, so sometimes what happens, these slopes are very susceptible to this rain induced erosion. Okay, whenever rain comes, this lot of mud slush is coming down from the slope. So what you can do to prevent that, we just place a geotextile layer over it, layer over the slopes. Okay, we place geotextile layer over the floor, what will happen, that will prevent the erosion of that soil to some extent. So geotextile covering, that can be say natural or synthetic. So natural means using jute and coir, that you will see those kind of things. And synthetic, you know, this PVC and all those kind of geotextile, both you can use. So there are some advantages, disadvantages. We will discuss that. Cellular mattresses and nets. Cellular mattresses means geocell. Geocell we can place over slopes also. We can place geocells. Then bitumen and asphalt space. So if we spray bitumen, that will actually prevent, it will hold the soil into the place, that will actually put, you can imagine, right, you can, it will actually make a hydrophobic coating kind of thing, right? So that will actually prevent the erosion. And the easiest method is vegetation, just by planting trees. So generally, why this erosion in hilly areas is like a major problem, that is because in the slopes, people are cutting down trees, they are cutting down plants to make houses and all those things. Due to that, what is happening? Due to that, total amount of vegetation is getting reduced. And so, whenever there is little bit of rainfall, the water is soil is loose, so the soil just gets eroded away. There is slope, it's getting filled. But if you plant more trees, the roots will hold the soil in position tightly, right? So that will actually prevent the erosion. Okay, so here there are many pictures that are given. So first, what is the first picture? If you can see, if you can guess, what is this first picture? What is this first one? This one, this first picture. What is this first picture? You can see a lake or some river, whatever that is, it is there. And we have the soil in this portion, right? This garden. To protect this area, we have put this graded boulders here. Okay, this is something but this riprap. Okay, this is nothing but riprap. Then Second, in the second image, you can see here this concrete lining, right? So we are lining this canal or whatever it is there with concrete so that this canal remains protected. Then we are having this connecting. So what we have here is that we have a slope. So high power gun, high pressure guns are actually used to spray concrete over this slope. So that this concrete goes and actually holds the soil in place. That is nothing but connecting. Then here we have this cells, geocells. These geocells are used over slopes. So we have a bottom soil is there, which needs to be protected. So what we do, we place geocell over it. We place geocell and then we fill that geocell with more soil. And now over that soil, what we can do, we can actually plant a grass or vegetation over there. So it will, the geocell will here will serve two purposes. One is protection, the protecting like protecting the soil that is underneath, and also it will act as a bed for plants to grow. Okay. So after that, after a few years, it will look very nice. Also, very green also. Those USLs are regularly used for these purposes. And here you can see this geotextile coverings. This covered large amount of geotextile covers are actually placed on the slopes to protect it. And here we have this gabion. So you can see these cages are there. Inside that, we are having aggregates filled to construct this gabion. So here also we have gabion. Here also this side also we have gabion. And water is flowing between. Okay. Then this vegetation, how actually vegetation provides. So what happens is the this root actually holds the soil very nicely. Right, this root actually holds the soil, and what happens due to that? Whenever there is rainwater, soil is not easily just taken away. Okay. Okay. Now we have a short question. Arrange the following soil types based on their erosion tendency from most erodible to least erodible. Okay, so we have to arrange the uh, following soil types from based on the tendency of most erodible to least erodible. So here, what do you think that which one will be the least erodible? Least erodible. Just a guess. Just by seeing, we can just say say. See, we know that if the size more, then it will be less erodible, right? So here, so first one is GP. So what is GP? What does GP mean? GP is poorly graded gravel, right? So GP should have the least tendency to erode, right? Because sizes are heavy, it's heavy, gravels are heavy. Okay, GP should have the least. Then we have SW, MH, ML, CL, SC. Okay, so out of these, the most erodible is actually silt. Okay, low plastic silt. Okay, then after silt, we have clay sand. Okay, after clay sand, we have this MH. This highly plastic silt. Okay, we have MH. After MH, we have ML already. It's fast. Then we have CL. Yeah. After MH, we have CL. that is low plastic clay. Then we have SW. Last we have polygated carbon. So if I have to write the total, it will be ml greater than sand, it will be C greater than greater than much greater than C or C greater than G. Okay. Okay. So before going to this part, so one more thing is that this coastal erosion. Right. So what happens? So due to the waves are hitting the shore like this. Right. So apart from that, there is some lateral drift of the waves also. Okay. Some lateral drift also is there. So due to this lateral drift also, what happens in the coast? Soil from one portion is transferred to some other portion due to the lateral drift also. So in one portion, this shoreline gets on reducing, and the other portion it gets on increasing due to this lateral. So to prevent that, so there are many things that are used. So one is we can use many types of breakwater and all those things, or cry this what to say groins. Okay, we can use these zigzag, these groins. We can use that's like barrier. So water is there. So just we can use this barrier. So what happens is this, so whatever erosion is occurring through this lateral drift of the waves that it gets prevented. Okay, let me just find some. Let's see, just a second. Okay, so we'll see some videos and pictures. Let us just finish this. Now, what is sustainable? What is sustainability actually means that however we are actually using things, using natural resources, whatever natural resources we are using, our future generations also should be able to use that. So we are to ensure that our future generations also have access to this sustainability. So geosynthetics can help in all aspects of sustainability. How? They reduce the requirement of natural construction materials like aggregate, soil, etc. So you already saw this, right? So this amount. So if we remember, we had discussed one topic uh, where we where we saw that with the use of geotextile or geograde, the thickness of unpaved road, thickness of stone aggregate in unpaved road gets reduced by large amount. So what that is sustainable construction, right? So you are able to use less amount of aggregates. Okay. Okay, you are able to use less amount of aggregates. With lesser amount of aggregates, we are able to achieve the same construction, okay, same strength in your in your whatever you are constructing. So that is what sustainability is. Okay, then promotes the use of locally available. Say you had to construct this reinforced reinforced earth wall, right? Reinforced earth wall, reinforced soil wall. So for that, whatever you can use the locally available. So if the locally available soil is fine, you can just use the locally available. So you need not bring very strong aggregates, where this very highly cohesionless high soil from somewhere else. Right. Understand, right? So we can just use an whatever it's available around us, because we can substitute that with a say we can use some we can increase the space strength of the we can make changes in the design, right? We can make changes in the design, so we can increase the strength of the reinforcement, we can provide some more amount of reinforcement, we can do these things. And what we can do, we can make use of the surrounding soil, whatever it is available, we can make use of that soil. Okay. Carbon footprint of most highway projects can be reduced by use of this. Obviously, so now that's why most of these approaches, bridge approaches or flyover approaches, those are all reinforced earth walls. None of them are concrete, right? Most of them are reinforced earth walls. So where if we use concrete, a huge amount of concrete will be required. That means more carbon footprint. So by constructing reinforced earth wall, you are reducing the carbon footprint by large amount. The natural geosynthetics can help in rural employment. So natural geosynthetics such as jute and coir, those are generally constructed by very poor, semi-skilled laborers in uh, poor villages. So this rural employment will be increased. Okay, the more amount of money will flow to the villages. Villages will grow. People in villages will also become rich. So that's why like geosynthetics are very useful to us. So mainly two main natural fibers are used for reinforcement, erosion control, drainage, filtering, or other purposes. Okay, there are mainly two main natural fibers that are used for reinforcement, erosion control, and other purposes. The jute and coir. So how do we get this? So jute fiber is actually obtained from jute plant. Okay, this image I have given here. This jute plant actually where we get this jute fiber. So jute fiber is like very common. So these ropes, jute ropes are used extensively everywhere, right? For all purposes, these jute ropes are used. Then jute bags are used, handbags nowadays. Very stylish jute bags are also available. So these jute bags are jute has very huge amount of uses. So now we also have this National Jute Board in India, which is actually promoting the use of jute fiber for to be used as geosynthetic. Okay. Uh, jute geotextile, jute this jute kind of geotextile, jute geocells, all those kind of things. Nowadays, these things are getting developed. The more usage of jute is actually very much beneficial. Okay, both to the nature and both beneficial to nature, sustainability, and also for us also because it will provide local employment to villages. Then we have coir. So how is coir? Coir is obtained from this coconut. Okay, coir is also extensively used nowadays for ropes, for making coir mattresses, and many varied purposes. Right. So we have to promote the use of this natural geosynthetic material. Now here some images are given where see first you can see this PVDs made up of jute and coir. Okay, and you can see stone column that is encased in bamboo grids. Then you can see coco logs for erosion control, right? Then we have coir mat. Okay, so you have a slope, you just cover that slope with the coir mat. So that will coir mat will prevent erosion, and also as it is a natural fiber, it will aid to the growth of vegetation, natural growth of vegetation in it. Okay, now as I was saying that this geosynthetic for erosion control, say now in a slope, you have a choice. You can use natural geosynthetic, or you can use say you have a slope, you have to protect that slope for erosion, okay, to prevent erosion. So there are two options that are available. One is the use of synthetic geosynthetic material, okay, synthetic geotextile, or you can use say this natural geotextile. So synthetic geotextile, these are made with plastics. What happened when we uh, put that synthetic geotextile? There may be possibility, means it is seen that It does not aid the growth of natural vegetation that much because it's plastic, so soil also cannot hold in it, hold over it. Cannot get a hold over it. Not soil, that's vegetation for hold over it. So in place of that, what we can do, we can put natural geotextiles such as made up of jute and coir. So jute fibers and coir fibers that will actually aid the growth of natural vegetation. Okay. But there are some problems like the life of this natural geosynthetics are actually much lesser. Obviously, they are much lesser than synthetic geosynthetics. So that we have to consider. Okay, so we will solve the problems. Three problems are there, so quite easy and straightforward problems. So we will try to solve them. Just just share the screen. Just a second. I will share the screen. Just a second. Just share the screen. Okay, so here, so this particular this video, you can see that. So we have a slope here, and see if you see this part, see so nicely this vegetation has grown over the slope, right? So see here we have the original slope. Over that we have put some geocell, and this geocell is actually filled with soil. Okay, and after that we will see that naturally after some time, very beautiful this vegetation has grown over it. Okay, you can see also this is the slope, and we have put the geotextile. So geotextile is geocell is laid like this, and it is actually anchored at this edge. Okay, on this side is anchored at this side. Similarly, here you can see this geocell is filled with gravel. See, you have a slope. We put the geocell, and then we fill with gravel. Okay, and after that, what you can do? You can have some roller runs over it, and you can have like a very nice road over it. Hmm. Then here it's one more. So let's just follow. So here you can see these are actually this jute or coir geotextiles. Okay, this jute or coir geotextile, they are using it for slope protection. So generally, see this is it is looking like this is a park kind of thing, right? So in that cases use we generally prefer this natural geotextile also, so that it aids the natural growth of vegetation over it. So this is the slope, and see how it is fixed. So we have these pegs, okay, steel pegs, and using these pegs you can easily fix it. So these are the rolls. So it is fixed at one end and just roll down. Okay, and at equal intervals it is packed into the soil. Okay, so you can see beautifully this coir geotextiles has been laid. Then you can see one more here, slope protection. So this is the anchor trench. Okay, you can see, this is a very big and vast slope. So you have the geotextile. This is the anchor trench. So we are putting this. This is the trench. Okay, this is the trench is there, and you are putting some amount of this geotextile into the trench. So that, and then after that we will cover that up so that this geotextile does not actually slide downwards. We put the thing, then cover the geotextile with slope. Okay, so this is the slope. We put coir geotextile over it. Then what you can do, you can put soil, and so that to aid the grass, what we can do, you can put seeds on it. There will be natural growth. Okay, there will be natural growth, see natural growth of grass over the coir. Just after a month, you can see grass has started to grow. Okay, just see total vegetation has grown over the geotextile slope. If both the purposes are served, one is it will look very good with green vegetation over it, and secondly, it will hold the soil also in position. Just one more thing. See some people videos. Uh, you can see these. These are nothing but gabions. Okay, these are put so that this erosion is prevented. So like this, similarly, many videos are there. You can see here also. See how it is placed. So these are what? These are these netted bags are there. Okay, these are just different things. So we have these bags here. These bags are actually filled with what? Filled with this aggregate. Directly, they are just putting the aggregate. You can see. All right. Now let us solve this problem. So evaluate the filtration adequacy of a candidate geotextile for placement beneath a rock riprap erosion control system in a coastal inlet area with 1 meter tides. It is reversing flow conditions with moderate water currents. Okay, as shown in the following sketch. The candidate geotextile laboratory properties are permittivity of zero point 0.5 second inverse and after opening size at 0.21 mm. The in situ soil is a beach sand which is Cu of 3.5, D 50.4, porosity 0.4. Okay, so uh, we need to evaluate the filtration adequacy of a candidate geotextile. Okay, first of all, you can see here that we have a geotextile that is dark black. So this dark bold black that you see here, that is the geotextile. Okay, the geotextile is placed, and over the geotextile we have the riprap. Okay, so the riprap is actually holding the geotextile in position, right? And also the geotextile has been anchored here. Okay, so this is the anchored trench. Anchored trench. So you see here the geotextile is anchored here, right? Anchored here, and over that you have a rock riprap. The riprap will actually dissipate the energy coming from the uh, this waves somewhat, and then this geotextile will actually hold the beach sand in its place. Okay, and whatever water is entering through it will just exit out easily. Can flow out easily, right? The in situ soil beach is a polygated sand with Cu and density and porosity dispersions. Okay. Now mean high water and mean low water, the difference in this uh, height is given. What we will do, first we need to find out the flow, adequate flow. Going to assume a water profile first. This is the geotextiles. Okay, this is the geotextile. Here we have sand. So this is the initial water and this is the final water. Okay, so this height difference is 1 meter. If you want to draw a rather phreatic surface, it will be something like this. Okay, and this is approximately estimated as 50 meters. All right. So Q max. So you are assuming that the tide will this tide will recede at maximum rate during the initial 2 hour period. All right. So here we have this system, right? We have this system. This bold black is the geotextile. This geotextile is anchored here in this anchor trench. The geotextile is anchored in the anchor trench. Over the anchor, over this geotextile, we have this riprap. This riprap will actually dissipate the water force coming from the water to some extent. And then what will happen? And also if you see one more thing, the slope at what this geotextile is placed, it's given 3:1. And also the mean high water to mean low water is given. That means the maximum water due to tides will be level is this one, and the minimum low water that is going here, that is this much. Okay, that is the water is actually fluctuating between these two portions. All right. The first task is to find out the total flow. Okay, flow that should be occurring. To find out that what they're assuming is that they are considering a portion. So this length they are considering 50 meter, and see 1 meter is the height. This is the initial water level. This is the final water level, mean low water level. So between these two, okay, between these two, this much portion, this water is playing. Okay, so if I extend this line here, just you are considering a section. Okay, okay, this is the geotextile. This is the geotextile. All right. So how okay. So we are assuming that this water, this flow of water, when the water is coming from 1 meter to the maximum tidal, okay, the maximum this the tide recedes at maximum rate, we are assuming that in the initial 2 hour period, the tides will recede. The water will flow through it in the maximum rate. Okay, so water level is here. So when the tide recedes, what the water is coming down, right? So here we have the slope. So initially water is there, and the water is here. This is the initial level. This is the final low water level. This is the high water level. This is low. We're assuming that this flow, that is water that is receding downwards, this recession of water, the maximum rate at which this water is going to recede, that what rate that rate at which the water is going to recede, that over the surface, this water is going to recede at the initial level is this, level is this. What the rate at which this water is receding, the rate is maximum during the initial 2 hours. Okay, initial 2 hours. Okay, so we are Q max as 50 into 1 into 1 by 2 average by 0.4 by 2. So 0.4 by 2, 0.4 is the uh, porosity and 2 is the time hours. Okay, so they are calculating this as 5.0 meter cube per hour, and this comes out as 1.39 second. Okay, so, so so this is the geotextile. This is the geotextile. So initially water was here, then water came here. So tide. This is the water recedes from here to here. Then we need to calculate permittivity. So what is permittivity? That is 1 meter times 3.16. Now, how am I getting this area is 3.16? Can you say how am I getting this area as 3.16? Say, see here this slope is given as 1:3, right? So just this portion, say for a 1 meter height portion. So water is receding through 1 meter. Okay, so for 1 meter high portion, this will be 3 meter, and in this portion, what will this is the length of the geotextile. How much will be L? L will be 1 square plus 3 square. Take bar 3.16. Okay, that's why this is 1 into 3.16 into 1. 1 means per meter length. Okay, so this one comes out as 0.0004. Now we find out that reliable reduction factor is 3%. So ultimate is given as 0.5. It's given in the question. 0.5 it's given. Zero point 0.505. How much? 10 into 1.2. So how much will be my factor of safety? Ten, which is acceptable, right? So this much is allowable and the required is this much. So allowable by required, I get the factors. Okay. So this is what this was what this is what this is the cross plane this permittivity, right? So this means the geotextile is will be able to allow the water to pass through it adequately. Right. So I hope you understand. This is a little critical. So here, like this, we have a geotextile place like this. So this is the high level, this is the low level. So when water actually recedes from here to this low level, this water should actually, that time this flow is occurring, right, to the geotextile. At that time, this flow is occurring to the geotextile out, right? So that much flow this geotextile should allow. Geotextile should allow this much flow to easily happen through it. Okay. While the water during the tides, during the tides, when the water recedes from high level to low level, high to low, the first is it is assumed that the maximum rate of recession is in the first 2 hours. Okay. So we find out the flow from that what is the rate of flow that will happen in 2 hours of time. That from that rate we found out the required this permittivity. So we're seeing that ultimately we find out the factor of safety is acceptable. That is the flow that will be occurring when the means the geotextile will be sufficient. This geotextile, the present geotextile that we are considering, that geotextile is adequate for or to allow to pass that amount of flow that will be occurring when the water recedes from this position to this position. That flow it will be able to allow that water to easily pass through it. Okay, the geotextile is sufficient, is really adequate for that water to pass through it. Okay. Now next is the what? This is the flow criteria. Next is the retention criteria. That means it should see now we found out that it is allowing adequate allowing whatever flow water is generated due to the lowering of water in the tides. That amount of water it is able to let out. The geotextile is able to let out. Now and we have to check that is the geotextile preventing the soil particles of the beach sand, whether is it arresting the passage of that soil particles of the beach sand or not. Okay, that we need to check. So here they have selected a criteria D50 should be less than D95, less than D90. So what is the D50 of the soil? 0.4. Did I write something wrong? Just a second. Ah, D50 is actually 0.10. Okay, and one more D90 is given as 0.0. Sorry. D90 is given at 0.10. Okay, and see what is the apparent opening size given 0.21. So 0.21 should be less. It is less than 0.400. Right. So okay. Right. That means the geotextile is able to satisfy both the flow criteria and our retention criteria. It is able to allow the water to pass through it adequately. Whatever flow is generated due to the tidal movement, that flow it is able to pass. And secondly, it is able to retain the sand beach sand in its position. Okay. One more thing, see, additional one more thing we have to check. This one I'm not talking. Uh, one more thing we need to check. What is that? The geotextile should not get damaged due to the lip trap. Understood. So reefs are huge size boulders, right? So you are placing the geotextile beneath the reef. So the reef should not actually puncture through the geotextile, right? It should not puncture, it should not damage the geotextiles. That we have to ensure. Let us see this. Determine the flow rate factor of safety of a geonet used as a primary leachate collection system above a geomembrane and beneath a sand covering layer in a landfill cell whose plan view is shown in the given diagram. A geonet delivers its flow to the central perforated heater pipe leading to a down gradient removal sump. A landfill is 35-meter high with a waste unit of 13 kilonewton per meter cube. The inflow rate is okay. So this is actually this drainage problem, right? So you have a landfill. The this plan view of the landfill is actually shown. The top view. So beneath the landfill, we have a perforated pipe. So the perforated pipe actually carries the, so we have a sloping ground like this. Here you have slope, this side we have slope. Okay, so this side we have slope, this side we have slope. In the center we have a perforated header pipe. Okay, so this geonet is actually placed along these slopes. This 2% gradient slopes along these slopes, this geonet is placed. Okay, the geonet carries the leachate. Okay, carries this whatever liquid, primary liquid leachate through this. Okay, carries along this slope, along this 2% gradient into the perforated pipe, and finally the perforated pipe drains it out to the removal sump here. Okay, so this geotextile we have to check. See the above this, so this is the plan view, and above this we have the landfill. Okay, above this we have the huge landfill. So if we have a landfill, the landfill is going to generate some leachate, that is some liquid. That, okay, from the whatever the solid waste or bio waste, whatever it is there, that liquid is actually nothing but the leachate. We have to drain that leachate out. So this is the ground. This is the ground. Above that we have 35-meter high landfill. Okay, landfill where all the everything is dumped. Below this, at the ground base level, we have this plan B, whatever is shown here, this drainage system. In this drainage system, we have slopes like this, like this. You have 2% gradient slopes, and in the center, we are having a perforated pipe. So leachate from all around will be carried by with the help of geonets in these slopes, and finally into the perforated pipe, and the perforated pipe will drain it into the removable sump. Okay. A design inflow rate is given, the height of the landfill and the waste, unit weight of the waste is given. So why is the height and the unit weight of the waste important? That is because we need to determine the pressure, particle pressure acting on the geonet. Okay, corresponding to that, you will get the flow rate from this chart that is given here. Okay, you can see the length here. Okay, so yeah, so geonet is, where is the geonet placed? Geonet is placed in this region, right? Okay, like it is carrying the leachate in this direction. It's carrying the leachate in this direction to this pipe, and the pipe is then finally carrying it out. Now, the length of the geonet should be maximum of these two. One is 25, and this we have to find out. So let us find this length out first. Okay, with this length, let us find out first. The maximum of the two, that will be the length of the geonet. Every degree, this is given 5 degrees angle is given. 5 degrees. 15 plus 13.1, 27.1. Okay. This length, this length is actually 27.1. So 27.1 is greater than 25. So we'll consider 27.1 as the length. The inflow rate is given in the question. 30,000 liters hectare day. Right. Now, how to convert liter to how to convert uh, liter to meter cube? How to convert liter to meter cube? 1 liter is how much? 0.001 meter, 10 to the power minus 3 cubic meter. How to convert hectare to meter square? 1 hectare is 10 to the power 4 meter square. Okay, so let us find that out. Is 0.003 meter cube per meter square per day. Okay, so this is the flow that is happening. Now now we need to convert the maximum flow per unit width. Is Q required is nothing but R into LH. Okay, 0.003 meter cube per day per meter square into 27.1 meter. This will give us 0.003 into 27.1 meter cube per day per meter. Okay, per meter width. Now, day from day will go to minute. 24 hours, each hour 60 minutes. Finally, it will be 5.645 to 10 to the power minus 5 meter cube per minute per meter. Understood? First of flow is given as meter cube, flow is given as liter per hectare per day. That we converted to meter cube per meter square per day. Then we multiplied by this length, we got it per meter width. So meter cube per day per meter. Then from day we went to minute. Okay. Now, vertical pressure. What is the vertical pressure that will be coming on the geonet? What is the vertical pressure that will be coming on the geonet? 35-meter high waste. So 35 into unit weight of the waste. 35 into 13. Corresponding to 455 kPa. And what is the gradient? What is the gradient along which this geonet is placed? What is the gradient along which this geonet is placed? It is 2% gradient, right? The geonet is placed along 2% gradient. 2% gradient along here. See, it's given, right? Around 2% gradient, this geonet is placed. So 0.02. So 0.02 corresponding to 0.02 and 455. Okay, corresponding to 0.02 and 455 approximately. From this graph, we can get the QS. Get Q ultimate as a meter cube per minute per meter. Okay. Now we get the Q allowable, Q ultimate by cumulative reduction factor 0.003, 10.4 they have taken. So it comes out as 4.885. What is the unit? Meter cube per minute per meter. Therefore, finally, factor of safety Q allowable by Q required 2.889. So by how much? What is the required? 5.645 10 to the power minus 5. So test 5.1, which is so the given GeoNet will be able to properly train out the digit. Okay, so I hope this was clear. Quite easy, simple problem. Same. First, find out the flow, required flow. Sorry, yeah, the required flow, then the allowable flow. Just divide them. We get the final. Now next problem. It is also a similar problem. Very simple problem. Assuming that there are no regulations governing the situation in the geonet, whose response is shown in the figure below, which is for the landfill land leak detection and collection system. The geonet lies between two HDP geomembranes and the design flow is 100 times de minimis leakage. We will see what de minimis leakage is. The minimum slope of the bottom of the 100-meter long landfill is 6%, and the landfill when completed will be 50-meter high with a unit weight of reaching 11. The same, okay, almost the same problem almost. So first one need to what we need to do, we need to find out the required flow. Right. So what? So required flow, it's given here. The design flow is 100 times de minimis leakage. So what is de minimis leakage? So I will just read it out for you. The primary or the upper geomembrane of a hazardous waste facility should allow no more than de minimis leakage of all polluting species through the inner line, through the liner itself. The coefficient of the concept of de minimis comes from the legal principle de minimis non curat lex. De minimis leakage is considered to be the amount that is of no threat to human health or the environment. Okay, it is considered that geomembrane, since they are not impermeable, will allow some transmission of waste constituents by such means as vapor permeation or by small impact. So, vapor permeation we will see next class. The actual level of de minimis leakage of a constituent is approximately 1.1, 10 liter per hectare per day. Okay. So de minimis leakage is nothing but this is the minimum allowable leakage that might occur. Okay, through a landfill liner into the surrounding soil. This is the minimum amount of leakage, minimum allowable amount of leakage that is allowed, minimum amount of leakage that is allowed to happen. So see it very little. So you have a landfill, right? Sorry. Say you have a landfill like this. So you will have some liner. So the minimum amount of leakage, okay, through the landfill that can occur into the surrounding soil, that is the de minimis leakage. That is just 10 liter per hectare per day. This is the minimum allowable amount of leakage. And we have to design the this system such that the maximum flow, this one that should occur into the drains. Okay, that is that the flow should occur to this 100 times that value. So that is here it is not actually both of them are related, unrelated, just to get the value they have given it like that. So Q required you will directly get it is what 100 times 10. 10 is what 10 liter per hectare per day 0.001 meter cube. Okay, then hectare is there meter square per day we get into minute, right? Right, times the length. This will come out as 100 meter cube per day per meter. If you till this much it was meter cube per day per meter square. Multiplied by length will give you per meter width. It is meter cube per day per meter. And will come out as 2.08 to 10 to the power minus 5. What is the unit? Meter cube per minute per meter. Okay. Now what is the vertical pressure? Again same similar vertical pressure 50-meter high, unit weight 11. So 50 into 11. What is the gradient? I. It's given here 6%. 0.6. Now from here, from this graph, we can approximately get the approximately it will be approximately somewhat here. So approximately we'll just get the value. Okay, value of Q ultimate. Then you have Q reliable, Q ultimate divided by RFs 0.01. Therefore, factor of safety is the required 2.08. Much will it be? This 53, which is more than actually more than 80 feet. Okay. All right. So this was all. Not many problems are there. They are very simple also, right? Just find out the Q, and there's just it and then determine the effects of safety. Very simple and normal also. Nothing exceptional here. All right. So with this, we will actually end. Yeah. So with this, actually, we'll end today's session. And before I go in the next class, let me discuss what we will be actually doing. So one thing we will be doing is that say this is the landfill. Okay, you are sorry. So say you are designing a landfill like this. These things we will discuss in the next class. So you will landfill. So here in the slopes, we will put some liner. Okay, let me just draw the slope. So this is the slope. Okay, So in the slope, what we have done is that we have put this geomembrane. So this is the geomembrane we have put. Now to cover the geomembrane, we need to put some soil covering over it, right? Of high thickness H. Okay, so this thickness H, or what, how much thickness of soil cover we have to provide actually, that we will find out. Okay, and if say if we have a geomembrane and over that say if you have one geogrid layer also, then how much will be this H? Okay, then how much will be this H? All these things, and not actually um, age. What we will be doing is that we will be finally finding ultimately finding out the factor of safety. Factor of safety of what? Factor of safety, so that this whole arrangement that you are doing. So you are placing the geotextile over that you are putting soil. Okay, over putting soil of thickness H. Okay, all these things, whatever arrangement you are doing here in the land to construct your landfill, you have to ensure that this is stable, right? So you will find out the factor of safety for this. We'll see how to find out the factor of safety for this. Okay, so that this condition is stable. Okay, this thing you will do, and one more thing you will do, how much this embedment length. Okay, how much embedment length should be there for the geomembrane? How much embedment length should be there? How much, if there is anchorage like this, if there is anchor, if the geomembrane is anchored, then how much length should be there? How much should be this? All these things we will discuss and try to derive it and then solve say some problems or whatever. Okay, all these things we will be doing in the next class. So this will be clear in the next class as we discuss everything. Slowly we will do on the next class, that is on the 17th. Okay, and after 17th we will have on 18th, probably on 18th we'll have a 1 hour summary session where we will from first to the end, we will just revise everything very fast. Within 1 hour we will do and we'll finish it. Okay, so with this we will end today's session. Thank you very much for attending, and have a good day, have a good evening, and thank you. Okay, hope to see you in the next session. Thank you. I hope today's problems were clear. Those were pretty straightforward and easy. So that should be clear. And I discussed the previous class, those problems also. Those were also pretty easy and straightforward. Just go through that, those ones. Okay. So with this, we will end this session. Thank you for attending.